Okay, well, in that case, welcome to the second day of the algebra session. And the first talk today is by Stephan Tornier, and he'll be speaking about think globally, act locally. Thanks, Stephan.
All right, thank you, James. Yeah, thanks for the session organizers for having me, and thanks for the conference organizers, I guess, to making it all work online in Zoomville and GatherTown. So yeah, I want to talk to you about what I've been up to over the last year, really. I spent a lot of time on this. So first, let me give you a quick 1-minute summary so you can still decide to go to another talk or have an afternoon nap. So I study automorphism groups of graphs, so combinatorial structures like this one and their automorphism groups. And so typically I'm interested in when these automorphism groups are big. So the graph should be fairly symmetric looking like this one. And in fact, it's best for me when they are infinite. So when I draw a graph that fades out towards the outside like this one, you have to imagine the regular pattern that you see repeating to infinity. Here's another example, a regular tree, a three regular tree in which every vertex has exactly 3 neighbors. So when I have a group like this, I equip it with a topology, namely the topology that comes from the action of the group on the vertices, the permutation topology. So in other words, 2 elements are close to each other if they agree on a large subtree, and something is close to the identity if it fixes a large part. So it's a topological group, and as such, it turns out to be locally compact and totally disconnected. And now, how do I study these groups? So I'm interested in global properties of these groups, such as transitivity properties for the action on the vertices, edges or paths or ends, or the normal subgroup structure of these groups. And now it turns out that there are strong theoretical links between these global properties of the group and local properties of the action. So what I mean by that is, if I have a group acting on this tree, I can take the stabilizer of a vertex, say the green vertex in the middle here, then the action of that vertex stabilizer induces a finite permutation group on the neighbors of that vertex, and also one on the neighbors at distance 2 of that vertex, distance 3, and so on. So I get a lot of finite permutation groups, one for every radius. And these tell me, and properties of these permutation groups are strongly linked to global properties of the group. And one of the reasons I do this too is these finite permutation groups lend themselves to computation. So in this talk, I want to mention a gap package that I've been developing for the last couple of months, which analyzes these local actions. And by the way, these all the pictures you see in this talk were generated using a web tool from one of our software support assistants, I guess, here in Newcastle, and you can find that on our website, among many other things. Okay, so that's the 1-minute summary. Now let's get into it. So usually I would include a slide on which I explain why I study these automorphism groups, but given that it's only a 20-minute talk, I won't do that today. You'll just have to believe me that there are good theoretical and practical reasons to study these groups. And if you want to know more, well, maybe just ask me later on in GatherTown. Okay, so next I want to just give you a glimpse at what exactly this connection between the local and the global structure is. And I don't need you to take the slide too seriously, but you just get the gist of it, namely that there is a connection. So suppose we have one of these totally disconnected locally compact groups, like the automorphism group of the regular tree. Then I make 2 definitions. The first one, this H infinity thing, is the intersection of all, I will call it big closed normal subgroups, groups that are co-compact, and the quasi-center, everything which has an open centralizer. And when we're talking about the automorphism group of a regular tree, for example, the first one works out to be the group that preserves the natural bipartition. So that's a subgroup of index 2. So it's fairly big. And this last thing here is trivial. An example where it's not trivial would be, say, a p-adic Lie group, then this works out to be the kernel of the adjoint representation. Okay, but yeah, don't worry too much about the details. So now here's a theorem from Burger-Mozes from the year 2000 and slightly generalized by myself in my thesis a couple of years ago. If you take a general locally finite connected graph, like the ones we saw on the first slide, and you have a subgroup of it, okay, that satisfies some, conditions that make it nice. So it's closed and non-discrete. And then more importantly, it's locally semi-primitive. So what that means is whenever I take a point stabilizer and I act on the neighbors of that point stabilizers, that permutation group is semi-primitive. And if you don't know what that is, it's something between transitive and two transitive. That just happens to be exactly the right thing for the following. So in that situation, under this local assumption, H infinity is minimal closed normal and co-compact in H. So it's a big subgroup. And the quasi-center is maximal discrete normal and non-co-compact. So it's a small subgroup. So I have this big one and this small one. And every other closed normal subgroup either lies above H infinity or below the quasi-center. In between, there are no closed normal subgroups. So you see that this local assumption of being locally semi-primitive has consequences for the normal subgroups, which is the global structure of the group. And in fact, this quotient, if I take H infinity mod its quasi-center, then because there are no normal subgroups in between, this group works out to be almost simple. So it has minimal closed normal subgroups that are topologically simple. And in fact, in most cases, it's even a direct product of these simple groups. So it's a strong structural result about this group. All right, so that's just to show you the relation between the local and global structure. Now let me talk about a particular class of groups acting on trees that takes this approach of starting with an action that you would like to see locally and trying to construct a group that acts on the whole tree with that property. So here's how that goes. Say you have a deregular tree, T3 in this case, and you have a vertex and an automorphism of this tree which sends X to somewhere else, Gx. And it does anything to the edges. You know, it could send the green one here to the red one there. I don't care. But I've colored this tree in such a way. Well, first of all, there are exactly D colors, and around a given vertex, you see exactly those D colors. And the reason I do that is, see, now I want to make sense to what I mean by the local action of G at this vertex. So I take another finite tree this time, which is independent from this regular tree, but it happens to be isomorphic to a ball of radius k inside TD. So I call that BDK. And let's call the center of that tree B. Then there is a unique color preserving homomorphism from this tree into the big one, which sends B to X. Okay, in this picture, it literally just takes the tree at the bottom and puts it upstairs. Then once I have that, I apply G. I'm still in TD. And from here, I can restrict myself to the K neighborhood of Gx and go back to the same tree BDK. And the automorphism of BDK that I get by going upstairs, around, and back down, I call sigma KGX. I call that the K local action of G at X. Okay, it's some automorphism of this group, of this tree BDK. And then the definition is, if I have any subgroup of this BDK, I take all the automorphisms of the tree, which at every vertex have the property that the K local action is in F, into one big collection. I call that UK of F, and it's a group acting on the tree. It's called the universal group for this local action because it turns out to be maximal among groups which have this local action. Okay, so that's In the case where k is equal to 1, this was introduced by Burger-Mozes 20 years ago, and then I generalized that to arbitrary values of k. So here's the definition again and some properties of this group. For example, whatever f I choose, it's always the closed subgroup of the tree. That's not too hard to see actually. If I have something that's not in this group, then that means that one of these local actions is not an f. And then that means if I take all the automorphisms which agree with this given one at that point, their local action is also not an f, so they're also in the complement. And then that's an open set. It's also vertex transitive for any f. Yeah, you can just take two vertices in the tree, send one to the other, and then do it in such a way that you act color preservingly. Then you're inside UK of f for every f. And it turns out to be compactly generated too, which is always good. But one of the questions about this group that I've had is take any f and now take a vertex in the tree. What is the action that the vertex stabilizer in UKF of x induces on the ball of radius k around x? You see, the problem is I'm allowing that local action to be anything in f. But the question is, do I really get everything in f? See, what could happen is that I have this group f and I take an element from it and act like that somewhere. And then for some reason, I'm not able to extend that to an automorphism of the whole tree using local actions only from f. That could happen. So that's a big question. And when a group satisfies that the local action is always exactly equal to f rather than just a subset of f, I say that it satisfies this compatibility condition C. So let me explain what this is exactly. Okay, so to explain how exactly this condition works, we need a suitable model for how to describe the automorphisms of these finite balls BDK. So here's B32. I have the center and I label its neighbors, say, by B1, B2, and B3. And I want to think of an automorphism of this thing as the collection of its one local actions at these four vertices. So one local action around B, one around B1, one around B2, and one around B3. So in other words, I have a map from odd BDK into odd BDK minus 1 semi-direct product and D copies of that thing again. And the map is really just, okay, you have something acting on the K ball. You look at how that acts on the K minus 1 ball. And for each neighbor, you take the K minus 1 local action of that. So this is not a particularly efficient description of this group because there's a lot of overlap between these local actions and they need to be compatible somehow, but it is the best description to shed some light on how exactly this condition C works. So with that, we have the following. For any F and odd BDK, we say that F satisfies C, not UKF, rather F satisfies C, if and only if, and it's an extension condition for every given element in F, and for every direction you could walk into, there has to be another element of F that's compatible in that direction. So here's what that looks like. For every direction and for every element in F expressed in this way, there has to be another one in F, which has the property that what used to be the action at the center is now the action in direction I, and what used to be the action in direction I is now at the center. And the other coordinates can do whatever they want, as long as they are compatible wherever these local actions overlap, and the whole thing ends up in F. So it's an exchangeability condition to some extent. Okay, and this kind of condition, so now we're interested in groups acting on these finite balls, F like F inside odd BDK, which satisfy this condition. And you can think about that theoretically and construct a few examples, but you can also implement it on a computer. And that's what I've done this year together with a maths and computer science student here in Newcastle. His name is Khalil Hannouch. So we've developed a gap package which can create, analyze, and find local actions with this compatibility condition for these universal groups. Okay, so it's all about these balls of a given radius in a deregular tree. And to make them manageable on a computer, first of all, I replace all the colors with labels. So instead of 3 colors, I now have labels 1, 2, 3. And again, every vertex sees exactly all 3 labels. And then to describe an automorphism of any of these trees, I also label the leaves in a sort of a lexicographic order kind of fashion. For example, the first leaf here would be the one where the path that I have to walk along to get there has the smallest possible numbers. So 1, 2 would be the smallest one. That's leaf number 1. 1, 3 is the second smallest, leaf number 2, and so on. So in this depth 3 tree here, I have 12 leaves altogether. Okay, so that's how I do this in GAP. And in fact, I want to show you maybe live in GAP what exactly that looks like. So here's my terminal. Can everybody see that on the right-hand side?
Yes.
So this is what it looks like in GAP. I have loaded this package. Oh, it's called Ugali, by the way, for universal groups acting locally. And it can do a whole bunch of things. So for example, first of all, I have to get a hold of these automorphism groups of the finite balls. So for example, odd B32, oops, forgot the semicolon, would give you the automorphism group of this middle ball here. It's something on 6 elements. And here are the generators of that group. For example, I could swap just 1 and 2, just 3 and 4, and so on. Okay, so that's this group. And now let's take a random element of this group. Here's 1. And let's see what is the local action of this element at one of the vertices. So for example, if I want the local action of that at the center, I'd have to type something like this. Vertices are addressed by the sequence of numbers that you need to get there. So in this case, the empty sequence. But I also need the information what tree this is a part of. So the 3 regular depth 2 case. And let's say I want the 1 local action of that thing. And it's 1, 3, 2. Okay, so if you look at this, 1 goes to 5, 3 goes to 2, and so on. You see it's a rotation this way, sort of. That's why the local action at the center is 1 goes to 3, 3 goes to 2, and so on. And what's the local action of that somewhere else? Maybe at the vertex that I get to by following direction 1. It's the same. Okay, that's unfortunate. Let's take something else where it's different. Here's a new element. Now that's also the same. It's unfortunate. There are elements where this does not happen. Okay, this one, for example. This automorphism of the tree has different local actions at the center and in direction 1. And now I can go back to this definition and ask the program to give me an automorphism which is compatible with the given one in one of these directions I. So that would look something like this. I'm in this 3 regular depth 2. F is my group. I want something compatible with A in direction 1, say, and let's call that B. No, I have to do it without the brackets. So it looks something. So 1, 2 is an automorphism. Okay. And apparently that, so that stops these two leaves, and apparently that should have the appropriate local actions replaced. So let's have a look. B has local action at the center, nothing, and in direction 1, 3, 2. So that's exactly the opposite of what I had before. That's what it means for two elements to be compatible in some direction. Okay, but then I said I'm interested, I might go 2 minutes over time here, that's okay. I'm interested in what are all the groups acting on one of the given tree that have this compatibility condition. So I could do something like this. Conjugacy class representatives of compatible subgroups on the 3-2 tree and the whole automorphism group, and then it tells me, okay, it outputs a bunch of groups. Actually, let's give a name to that. Let's call that list. And then what's the size of that list? Okay, there are 9 groups. And now maybe if I want to learn something about these groups, I could, maybe I'm interested in, okay, they all act on this tree, but what do they do on the inner level? What permutation group do they induce on just the inner leaves? So I could do something like, for H in this list, do something and then finish doing. It's one of these programming languages where you finish do with odd, and then print something. And what do I want? Maybe the image of the projection of this group H acting on the 3-2 ball, and then a line break. Okay, let's see if this works. No. Okay, I have to tell it which projection I want. I want the one to level 1. Okay, so here we go. These 9 groups. The first one just acts like nothing in the middle. The second one is S2, if you like. Then here's something with A3 and so on. So this is the kind of thing you can do. You could also ask, among the groups in this list, which of them produce a discrete universal group? These groups are always totally disconnected, but sometimes they're discrete. So that's something interesting. And I've implemented that. It has to do with certain stabilizers in this subtree. And you'll see that some of them are discrete and some are not. And then the discrete ones, for example, you can relate them to the Weiss conjecture. They are all examples of groups that are studied in the context of that conjecture. Okay, so I'm already over time. Maybe I'll stop there. So let me just say, so this package has appeared on GitHub a month ago. You can check it out here. And it's currently in submission. But if anything like this or something similar seems interesting to you, please get in touch. I'd be very interested to hear about it. There's also a good manual. We've put some effort into that. And if I could just take another 30 seconds for a small advertisement. So for, as part of a DECRA fellowship over the next couple of years, I'm planning to generalize this class of groups and study it, try to generalize both the theory and the implementation for this class of groups. And as part of that, I'll be looking for a PhD student. So if anybody knows someone who might be interested in working in this direction, please get in touch. Okay, I'll stop there. Thank you.
Okay, thanks very much, Stephan. Any questions for the speaker?
Yeah, I have a question.
Yeah.
So would this be something you could set running to look for counterexample to Weiss conjecture?
Well, no. So the Weiss conjecture says there are only finitely many conjugacy classes of, discrete, vertex transitive, locally, blah, blah, blah. Okay, but you could keep it running for larger and larger radii, but you would never know if,
Yeah, okay.
You cannot output infinitely many things. But you can at least find a lot of examples and maybe confirm computations that other people have done with finite graphs and local actions there. Yeah.
Nice. Very ugly. Very ugly.
No. That it's ugali, like the African maize flour porridge, but with Y instead of I.
Okay.
I've got a question, if that's all right.
Yes, Florian?
Have you're asking about things like you've got local information on a group and you want to know if it extends to a global automorphism or something like that. Have you thought of casting this in the language of sheaves and pre-sheaves?
I have not. No, I have not.
It might possibly be a natural language for that. So you view your tree as a topological space, on that you define a pre-sheaf of groups that somehow to each open subgroup assigns maybe the automorphism group or the subgroup of automorphism that act in a certain way. Is this pre-sheaf actually a sheaf, which means if you have local things that are compatible, do they combine to form a global thing?
Right. Yeah, it's it definitely goes in that direction, trying to stitch together local pieces to something global. Yeah. Maybe we should talk about that sometime later.
Well, in the interest of time and transferring speakers, smooth transition of speakers, we might call the questions off there. Let's thank Stephan again, though.
Thank you.